This video will describe CNN-Cert, an efficient framework for certifying robustness of convolutional neural networks. Neural networks have become increasingly popular for a variety of tasks, most notably classification. However, they're susceptible to adversarial attacks, which is when the input to a neural network is slightly perturbed in order to cause a misclassification. As illustrated here, a panda is classified as a gibbon when an imperceptible adversarial perturbation is added to the image. This has serious consequences in applications like self-driving cars, where adversaries could cause accidents. So, what can be done? One thing we can do is to quantify robustness to adversarial attacks. To do this, consider the space of inputs to a neural network. The green ostrich is a correctly classified point. By moving in the direction of decision boundaries, we can find adversarial examples. Ideally, we would like to know the minimum distortion necessary for misclassification, represented by the black circle, since it represents a measure of robustness. Unfortunately, finding the minimal adversarial distortion is computationally infeasible, especially for large neural networks. Instead, we can find a lower bound on the minimal adversarial distortion, represented by the green region. Any perturbations within this green region will not change the classification of the image. A number of works have already attempted to find lower bounds on minimal adversarial distortion. Clever is a method that finds robustness estimates for general neural networks, including convolutional neural networks, or CNNs, a type of neural network that has become popular for image-related tasks. However, Clever only provides a robustness estimate. It cannot guarantee that perturbations within a certain radius are safe. Fortunately, some techniques do provide guarantees. One such technique is FastLin. FastLin works on multi-layer perceptrons, or MLPs, also known as fully connected networks. FastLin works on networks with the ReLU activation. Crown extends this to networks with general activation functions. However, both Crown and FastLin don't support networks with more general structures, such as pooling layers. This motivates us to introduce CNN-Cert, a framework for certifying robustness on general convolutional neural networks. Like FastLin and Crown, CNN-Cert provides a robustness certificate rather than an estimate. We also note that other teams have developed methods similar to or equivalent to FastLin and Crown, including DeepZ and DeepPoly. Next, I will go through how existing methods handle CNNs. Existing methods require converting CNNs to the equivalent MLP. In this example, this requires converting a small 2x2 convolution into a much larger fully connected weight matrix. This has two computational disadvantages. First, storing these larger fully connected weight matrices requires more memory, and operating on these larger weight matrices requires more time. This makes this pathway less efficient. Our proposal, as we will show, can operate directly on the CNN without the need for conversion, so it is efficient. CNN-Cert's efficiency can also be seen from a computational complexity standpoint. Given a CNN with an R by R input, certifying directly on the CNN requires in the order of R squared time, while certifying on the equivalent MLP requires on the order of R to the 6th time. For CNNs with large input sizes, using CNN-Cert can be dramatically more efficient than using an algorithm like FastLin. As mentioned, CNN-Cert is also general. It can support CNNs with a variety of building blocks, including convolution, residual blocks, and pooling, as well as general activation functions. It is also important to note that any MLP can be converted into a CNN, so CNN-Cert is strictly more general than an algorithm like FastLin. Next, I will walk through how algorithms like FastLin and CNN-Cert operate. The input to the algorithm is a trained network with fixed weights and a particular input. The first step is to guess a perturbation size epsilon and check if the perturbation size can be certified to be robust or not. To do this, we find lower and upper bounds at the first layer of the network. Using the first weight matrix, we can then find upper and lower bounds at the second layer of the network. For subsequent layers, bounds are found using the weight matrices up to that point. Here, quantities are propagated from the third layer to the first layer, which allows us to find bounds at the third layer. This process continues until bounds are found at the network's last layer. At this point, we can check if the image can be certified with the perturbation size epsilon. If the lower bound of the correct class is higher than the upper bound of the target class, then we can guarantee that the classification won't change. We can then use binary search to find the largest perturbation size epsilon that can be shown to be robust. So, what makes CNN-Cert different from existing algorithms? The key lies in how the bounds are represented. Given a network f of x, FastLin bounds the network with two linear functions, ax plus b, which are essentially two parallel hyperplanes. Crown changes this by making it not necessary that the two hyperplanes are parallel, but the bounds are still in the form ax plus b. CNN-Cert represents bounds in the form a convolved with x plus b. This is what allows CNN-Cert to be more efficient than existing algorithms. Next, I will describe convolution bounds for particular layers. This shows bounds on an activation convolution block, given by the input-output relation shown here. The bound on this layer is in the form a convolved with phi plus b, where a and b are functions of the layer's parameters. Similar bounds can be found for batch normalization, max pooling layers, and residual blocks. In all cases, the bounds have the same form, a convolved with phi plus b. The only difference is in the a and b values. Indeed, any layer that has bounds of this form can be incorporated into our framework. Currently, CNN-Cert supports convolution, batch normalization, residual blocks, and pooling. CNN-Cert can support networks with any combination of these building blocks, including pure CNNs, LeNet-like networks which have pooling, and ResNets. Next, I'll go through some results. This table shows certified perturbation sizes found by CNN-Cert and other methods. Higher bounds mean a larger region can be certified, so larger is better. As illustrated, CNN-Cert achieves similar or better performance than other methods. In particular, it achieves about a 20% improvement over the FastLin method. While CNN-Cert finds similar or better bounds in existing methods, it can find these bounds much faster. This table shows the run times to compute certified bounds. As shown, CNN-Cert finds bounds about an order of magnitude faster than FastLin and Deep Poly, and 2 to 3 orders of magnitude faster than the LP method. We also note that some other methods cannot support certain networks, as indicated by the green X's. Some methods are also computationally infeasible for large networks, as indicated by the blue stars. To conclude, CNN-Cert finds a certified region of robustness, such that any perturbations within this region won't change the classification. CNN-Cert is general, allowing for a variety of structures and activation functions, and it is efficient, directly applying certification to CNNs without the need for conversion to MLP.